Hello, welcome to our presentation titled Revisiting Batch Normalization for Improving Corruption Robustness. Deep learning has shown unprecedented performance in various vision tasks. Prior works show that common corruptions, such as Gaussian noise, can decrease the performance non-trivially, causing critical concerns for the need to improve corruption robustness. In a parallel line of research on domain adaptation, an unlabeled target domain dataset is exploited to improve the model generalization capability to a target domain. Broadly speaking, the clean images and corrupted images can be seen as coming from different domains. Despite this conceptual similarity between domain adaptation and corruption robustness, the community tends to treat them as two distinct issues. Domain adaptation usually has a predefined target domain with unlabeled dataset, while corruption robustness normally does not assume such a predefined corruption type. One straightforward solution to improve the corruption robustness is by performing data augmentation with corrupted images during training. The limitation of this solution is that a model trained on images of a certain corruption type might be vulnerable to another type of corruption. In domain adaptation, there is a line of work adapting the feature statistics instead of adapting features. Prior work hypothesizes that the label-related knowledge is stored in the weight matrix of each layer, whereas domain-related knowledge is represented by the statistics of the BN layer. They transfer the trained model to a new domain by modulating the BN statistics. In this work, we interpret the corruption robustness as a domain shift problem and propose to rectify BN statistics for improving model robustness against common corruptions. The BN statistics are estimated and adapted on as little as 32 representation samples from the new corruption domain. In practice, it is not challenging to obtain a reasonably small number of representation samples. For example, in the scenario of autonomous driving, weather conditions can change from day to day but tend to be consistent over a shorter time frame. Thus a system can capture a few unlabeled images as the samples to represent the new weather after a significant change in the conditions. On ImageNet-C, statistics adaptation improves the top 1 accuracy of RASNet 50 from 39.2% to 48.7%. Moreover, we find that this technique can further improve state-of-the-art robust models from 58.1% to 63.3%. Specifically, we rectify the BN statistics by randomly selecting a batch of 32 representation samples from the corruption dataset of the respective severity. We use the mean corruption error and the top 1 accuracy as the metrics to evaluate the efficacy of our approach. BN can be intuitively understood as normalizing a batch of samples with different contents to be centered around a single style. With this understanding, the population statistics represent the style information instead of the content information. We verify this hypothesis by measuring the absolute difference for BN statistics under different network inputs. We find that different batches coming from the same distribution have very similar BN statistics. Comparing batches coming from clean and corrupted samples, a greater difference in the BN statistics can be observed. To motivate our approach, we showcase the influence of input corruptions on the BN statistics. To measure the shift caused by corruptions, we treat each feature output as a vector and adopt the cosine similarity between the feature output of a clean batch and a corrupted one and average over the batch size. With increasing severity, the cosine similarity decreases, indicating a greater deviation of the two feature layer outputs. Rectifying the BN statistics improves the cosine similarity values for all severities. Here, we show the performance of our approach on Cipher10C and Cipher100C datasets. On Cipher10C, we find that our approach helps improve the model accuracy by around 10 percentage points. A similar trend is observed for Cipher100C. We observe that models with higher capacity exhibit a higher initial accuracy and show a higher performance increase. This significant performance improvement is also observed for models trained on the large-scale ImageNet dataset. Additionally, our method further improves models originally optimized for corruption robustness by a large margin. Adversarial training improves the initial robustness significantly on Cipher10C, and our performance can still boost its performance by a non-trivial margin. On ImageNet-C, a great performance boost on adversarially trained models is observed. For example, our approach improved the accuracy from 31.1% to 46.9%. In this work we argued that feature statistics can be interpreted as the style instead of the content. This observation led us to rectify the BN statistics to improve model robustness against common corruptions. We showed that rectifying the BN statistics can significantly improve the corruption robustness over several benchmark classification datasets with a wide range of seminal models. For an extensive analysis, please refer to our paper. Thank you for your attention.